Hello students, how are you all? Let's take another interesting topic of organic chemistry, that is reaction mechanism. Children, this topic, reaction mechanism, is a very important topic as far as board exams are concerned, and for sure you get a 2 or a 3 mark question related to this topic. So in this topic, we will be dealing with the 5 different types of reaction mechanisms which we will study in the organic chemistry content of class 12. Let us start with, from the chapter haloalkane and haloarine, the substitution nucleophilic unimolecular and substitution nucleophilic bimolecular type of mechanisms. Let me tell you children that the characteristic reactions of haloalkanes and haloarines are nucleophilic substitution reaction. Now here, let me make it clear what do we mean by nucleophilic substitution reaction. See, a nucleophile is an electron-rich species, so whenever a halogen leaves the alkyl halide, then that halogen is replaced or substituted by the incoming nucleophile, and such type of reactions are called nucleophilic substitution reactions. These reactions are of 2 types, as you can see. Substitution nucleophilic unimolecular called SN1 reaction, SN1 mechanism, and substitution nucleophilic bimolecular called SN2 mechanism. Okay, so let us start with the very first mechanism, SN1, substitution nucleophilic unimolecular. Let me tell you first that it is a 2-step process. That means proceed in 2 steps, and the order of reactivity of the alkyl halide towards SN1 is 3 degree alkyl halides are more reactive as compared to 2 degree as compared to 1 degree towards SN1 mechanism. So in detail, let us discuss that how this mechanism proceeds. The step 1 will involve the hydrolytic cleavage of a 3 degree alkyl halide. Since I told you that 3 degree alkyl halides are more reactive towards SN1 mechanism, we will discuss why when we study the first step of the mechanism. Hydrolytic cleavage of 3 degree alkyl halide involves the breaking of the carbon-halogen bond in the presence of protic or polar solvents, and this step results in the formation of an intermediate carbocation along with the halide ion, which is actually called the leaving group. The carbocation intermediate which is formed, we all have discussed in class 11 that the order of stability of the carbocation is 3 degree carbocation is more stable than 2 degree than 1 degree. Because of the formation of a 3 degree carbocation, the order of reactivity of the alkyl halides towards SN1 follows 3 degree more reactive than 2 degree than 1 degree. The reason is because 3 degree carbocation is more stable on account of greater hyperconjugation. This you have already studied in class 11. So the first step, remember, is a slow step, and slow step is considered to be the rate determining step. The second step involves the attack of the nucleophile on the carbocation. See, the carbocation has, the carbon in the carbocation has sp2 hybridization and it has a trigonal planar geometry. This trigonal planar geometry of the carbocation allows the nucleophile to attack not only from the back side called rear attack, also from the front side with equal probability or possibility of 50%. So, the nucleophile, because of the trigonal planar geometry of the intermediate carbocation, can attack from rear side as well as from the front side. Now let us see what if it attacks from the back side, rear side. If it attacks from the back side, then the phenomena involved is called inversion of configuration. But when it attacks from the front side, it is called retention, and both these phenomena occur with equal possibility of 50-50%, resulting in the formation of 50% of the dextrorotatory isomer and 50% of the levorotatory isomer. That means you get an equimolar mixture of the 2 dextro and levorotatory isomers. Now, what do we mean by dextro and levorotatory isomers? These are actually the optically active compounds which have the ability to rotate the plane polarized light either towards left if it is levorotatory or towards right if it is dextrorotatory. So, what do we obtain is an equimolar mixture that is 50% of the levorotatory isomer and 50% of the dextrorotatory isomer. This equimolar mixture is called racemic mixture. We call it as a racemic mixture, and remember that racemic mixture is optically inactive. Let me tell you the reason that why this is optically inactive. Optical inactivity means the inability to rotate the plane polarized light. Despite of the fact that it is comprising of the two enantiomers, dextro and levorotatory isomers, yet it is not able to rotate the plane polarized light. Let us see why. It is so because if 50% of the levorotatory isomer is rotating the plane polarized light on the left in the left direction, the dextrorotatory isomer is doing in the right direction with the same angle. The net result is that the optical rotation in both the left and right directions cancel out and the net rotation becomes zero. That means this phenomena is called external compensation. Please note down external compensation, which makes this racemic mixture optically inactive. So I hope it is clear that what is SN1 mechanism all about. Let us now see the SN2 mechanism, substitution nucleophilic bimolecular. After studying SN1, we are going to study SN2 mechanism. Let us see that what are the characteristics of this mechanism. It is a single step process, occurs in only one step. The order of reactivity for alkyl halides towards SN2 mechanism is 1 degree more reactive than 2 degree than 3 degree. Why so? We are going to discuss in a short while. In case of SN1, SN2 mechanism, which is actually a single step, the nucleophile attacks from the rear side. Now look at the structure. This alkyl halide is a 1 degree alkyl halide. 1 degree alkyl halide basically are more reactive since there is less steric hindrance in case of 1 degree, whereas in case of 3 degree, which are least reactive, the 3 bulky alkyl groups attached to the carbon makes greater steric hindrance and do not allow the nucleophile to attack easily. Now in this case, the nucleophile attacks from the rear side, resulting in the formation of intermediate transition state. Now transition state basically is a pentavalent state where you can see the carbon halogen bond shown with the dotted line and even the carbon nucleophilic bond, which is a new bond going to be formed, again shown with the dotted line. After this, Walden's inversion occurs. Why inversion? Because the nucleophile attacked from the rear side, resulting in the formation of a product with inverted configuration. What do we mean by the product with inverted configurations? See, in this alkyl halide, the halogen was attached on the front side, but because of Walden inversion, the nucleophile has joined the rear side or the back side since it attacked from the rear side. So this was the brief description about SN2 mechanism. Now, in a nutshell, let us see differences between SN1 and SN2 so that quickly we can get a recap of the two mechanisms. The SN1 mechanism is unimolecular, that means molecularity of this mechanism is 1, whereas SN2 is bimolecular, means the molecularity of this is 2. Molecularity refers to as the number of colliding species in a reaction. It is a first order reaction. SN1 is a first order reaction. Now why it is a first order reaction? Look at the first step of SN1, which involved the heterolytic cleavage of 3 degree alkyl halide. And since this step is a slow step is considered to be the rate determining step, responsible for predicting the order of the reaction. Since only one species is participating in this, therefore the order of the reaction is 1. Whereas for this the order is 2, since the rate is not only dependent upon the concentration of alkyl halide but also on the incoming nucleophile. Let us see the second point of difference. It occurs in 2 steps and this SN2 mechanism occurs in single step. The order of reactivity for SN1 is 3 degree alkyl halides more reactive than 2 than 1, but reverse order is applicable for SN2 mechanism. The reason being, again we studied that 1 degree alkyl halide will offer minimum or least steric hindrance. In case of SN1, the intermediate formed is a carbocation. You can see a carbocation is being formed. Whereas in case of SN2, the intermediate formed is transition state. A transition state is being formed. In case of SN1, another difference, the attack of nucleophile occurs from both sides. The reason being the trigonal planar geometry of the intermediate carbocation. Whereas only rear attack is possible in case of SN2 mechanism. The reason being in front side, greater steric hindrance is offered for the attack of the incoming nucleophile. Next, let us see the process involved. In case of SN1, both retention and inversion are involved. On account of 50% possibility of the incoming nucleophile to attack from the front side and 50% to attack from the back side. But in case of SN2, only rear attack is possible. And Walden's inversion occurs in case of SN2. In case of SN1, there is a formation of a racemic mixture, that is an equimolar mixture of the two dextro and levorotatory enantiomers. Whereas in case of SN2, a product of inverted configuration is formed. Last, most important difference, that SN1 occurs in case of protic solvents and SN2 occurs where the reactions involve non-protic or aprotic solvents. The next mechanism in the series is from the chapter Alcohols, Phenols and Ethers. We are going to study 3 mechanisms from this. The very first mechanism is acid catalyzed hydration of alkene to form alcohol. Alkenes, we all know on hydration. Hydration means addition of water. Acid catalyzed means in the presence of H2SO4 concentrated. This hydration occurs resulting in the formation of alcohol. So let us study the 3 steps involved in the mechanism. The very first step is the protonation of alkene to form the carbocation. Now what happens is that this water reacts with the H plus ion, resulting in the formation of hydronium ion. This H3O plus ion is called hydronium ion. Now this hydronium ion attacks on the alkene and this H plus ion of the hydronium ion goes to alkene, resulting in the formation of a carbocation. Carbocation is a carbon species bearing positive charge. It results in the formation of carbocation along with water. Now the step 2 involves, once the carbocation is being formed, the step 2 involves the nucleophilic attack of water, that is the phenomena of hydration on the carbocation. This water now attacks on carbocation, and when it attacks on carbocation, the oxygen which is having its 2 lone pair, it forms a coordinate bond with the carbon bearing positive charge of the carbocation. This species which is now formed in the second step is called protonated alcohol. This protonated alcohol means alcohol to which extra proton gets attached. This is called protonated alcohol. So this protonated alcohol in the last step, which is actually deprotonation, removal of proton. It results in the formation of alcohol, and let us see that this protonated alcohol which was formed undergoes deprotonation. Removal of proton occurs from this so that it results in the formation of alcohol along with the hydronium ion formed as the byproduct. So let me just recall and revise once. Mechanism of acid catalyzed hydration of alkene to form alcohol involves the 3 steps. Protonation of alkene to form carbocation. Carbocation which is formed on that carbocation attacks the water, resulting in the formation of protonated alcohol, which then in the last step, step 3, undergoes deprotonation to convert finally into alcohol. So this was the mechanism of acid catalyzed hydration of alkene. Let us now move on to the second mechanism, which is acid catalyzed dehydration of alcohols at a temperature of 443 Kelvin to form alkene. Remember, the temperature is very, very important here, since at a temperature of 413 Kelvin, alcohols on dehydration do not form alkene, rather form ethers. So if the temperature 443 is mentioned, you have to convert the alcohol into the corresponding alkene as a result of dehydration. So this is the overall reaction, that is ethanol we have taken. It is reacted with H2SO4 concentrated. The role of this is to act as a dehydrating agent. And at temperature 443, it results in the formation of ethene. So this mechanism also involves 3 steps. Step number 1 deals with protonation of alcohol to form protonated alcohol. See, H2SO4 which we have taken breaks to release H plus ion, that is proton, along with HSO4 minus ion. This proton which is released as a result of breaking of H2SO4 attacks on alcohol, resulting in its protonation, forming protonated alcohol. Extra proton is attached on the alcohol, forming protonated alcohol. Step 2 involves the dehydration of the protonated alcohol to form the intermediate species carbocation. Now just see, this is protonated alcohol. It undergoes dehydration, loss of water. Now what happens? This bond will break and will generate a lone pair back on oxygen, resulting in the formation of water, and the species carbocation will be formed in the second step. The step 3 deals with deprotonation, that is removal of proton of the carbocation, resulting in the formation of alkene. So deprotonation occurs, and just see that this proton is being lost, so that this bond basically goes here and generates a double bond between the 2 carbon atoms, resulting in the formation of alkene as the major product. The H plus of the proton which is lost combines with the counter HSO4 minus ion to regenerate H2SO4 back in the reaction. The last mechanism in this series is acid catalyzed dehydration of alcohol to form ether. This occurs at a temperature of 413 Kelvin. Just now we discussed that alcohols on dehydration at 443 Kelvin result in the formation of alkenes, whereas at 413 Kelvin they form ethers as the major products. Now, if you look at this mechanism, involves 4 steps. All the mechanisms discussed earlier involved the 3 steps, that is acid catalyzed hydration of alkene to form alcohol, 3 step, acid catalyzed dehydration of alcohol at 443 to form alkene, also 3 step. But this mechanism, dehydration of alcohol at 413 Kelvin, involves 4 steps. Now to just remember, the first 2 steps are just the same. Just the same that we discussed at a temperature of 443 Kelvin. The first step, let us revise again. The first step involves the protonation of alcohol to form protonated alcohol. This H2SO4 releases H plus ion. This proton gets attached to the oxygen, bearing a lone pair of alcohol, resulting in the formation of protonated alcohol. Here also we had seen in the first step formation of protonated alcohol. The second step deals with dehydration of protonated alcohol to form carbocation. This step is also similar to step number 2 here, dehydration of protonated alcohol to form carbocation. So this protonated alcohol removes a proton, removes water molecule, undergoes dehydration, resulting in the formation of carbocation. Now the third step is different here, and this involves the attack of the carbocation on alcohol. Actually, alcohol here taken is in excess, and alcohol, when the carbocation attacks on alcohol, it results in the formation of protonated ethers. Protonated ethers in the final step, last step, undergo deprotonation, removal of proton, resulting in the formation of ethers as the major product. This occurs at a temperature of 413 Kelvin. So I hope this mechanism is clear, and the first 2, step number 1 and 2, are just common to the mechanism of acid catalyzed dehydration which we discussed at 443 Kelvin. The third step involves the attack of the carbocation on alcohol to form protonated ether, and finally deprotonation of protonated ether to form ether.